In this video, you will learn about working principle of an electromagnetic relay. This is a small typical electromagnetic relay which is most commonly used in many applications. The main components of the relay are an electromagnetic coil, an armature, a spring system, a yoke, and fixed and movable electrical contacts. In electromagnetic coil, a coil of wire is wound on a soft iron core. It is used to generate the magnetic field to the soft iron core. The yoke is used to provide a low reluctance path for the magnetic flux produced by coil. The movable iron armature is hinged to the yoke with spring arrangement. One or more sets of moving electrical contacts are mechanically linked with the movable iron armature. Due to this arrangement, when the relay is in de-energized condition, there is an air gap between the armature plate and core. In this condition, some of contacts would be in closed condition. These contacts are called as normally closed contacts or NC contacts. And some other contacts would be in open condition and they are called as normally open contacts or NO contacts. Note, the type of contacts NO and NC are described with respect to the de-energized state of the relay. When supply is provided to electromagnetic coil, it generates a magnetic field. So the armature is attracted towards the electromagnet core. The consequent movement of the movable electrical contacts break the NC contact connection and they move to open condition. Simultaneously, the NO contacts move and their contacts get to closed condition. When the current flowing the electromagnetic coil is switched off, the relay coil gets de-energized. Then the armature is returned to its original position by the spring arrangement. Hence it restores the contacts to the normal condition with NO contacts open and NC contact closed. Now you have learnt about working principle of an electromagnetic relay.
The magnetic flux produced in the unshaded portion of the electromagnet is minuscule too. The shaded portion of the flux pi1 is 40 to 50 degree lagging with the unshaded portion of the flux pi2. The two alternating fluxes pi1 and pi2 induce two voltages V1 and V2 on the disk. These two induced voltages V1 and V2 create eddy currents I1 and I2 on the disk. These two eddy currents produce a deflecting torque on the disk. This deflecting torque is directly proportional to the square of the current to be measured, that is Td alpha I square. The disk rotates depending on the residual torque between deflecting torque and the spring action and attains a balanced position. This position is graduated against the actual pointer reading of the parameter. When the disk rotates, it cuts the magnetic field generated by the permanent damping magnet. Hence, eddy current is induced in the disk which interacts with field of the damping magnet and produces a torque in the opposite direction to deflecting torque. Now you are going to see the phasor diagram of shaded pole type induction instrument. The vectoral sum of two magnetic fluxes pi1 and pi2 gives the resultant magnetic flux pi. These two fluxes pi1 and pi2 induce the voltages V1 and V2, which are in 90-degree phase shift with the fluxes pi1 and pi2 respectively. The two voltages V1 and V2 induce the eddy currents I1 and I2. Each eddy current is lagging by an angle alpha with the induced voltages. Thus, you have learnt about the construction, working and phasor diagram of a shaded pole type induction instrument.